Next and last title in chapter 4, section 2 is force vibrations and resonance. Okay, now look at the board. As you see, there are 1, 2, 3, 4 pendulums. In these 4 pendulums, 2 of them same in length. They are colored by blue. Green one is longest in length. Red is shortest in length. And in chapter 3, section 2, we learned that frequency of vibration of any pendulum depends on its length. Let's remember the equation. F is equal to 1 over 2 pi root of G over L. Yes, G over L. As length is increasing, frequency of the vibration decreases, or vice versa. Because these pendulums are different in length, 2 blue are equal in length, but the rest of them, they will have different vibration frequency. So I'm going to label the pendulums A, B, C, and D. A and C, they are the same in length, they have the same frequency of vibration. When you swing them, they will start vibrating with the same frequency. But B is longest. Longest means smallest vibrational frequency. It will vibrate slowly. But D, shortest pendulum, it will vibrate the fastest. And these pendulums are attached to each other by a rubber band. This is a rubber band, which is going to be used for transferring the vibration from one pendulum to another pendulum. Okay. The frequency of each pendulum depends on string length. Yes, we know it. And does every pendulum will vibrate at a certain frequency. This frequency now, in this title, we are going to name as natural frequency. And when you swing them, at what frequency that object will vibrate, it is called natural frequency from now on. A and C have the same natural frequency, but B and D different. So, red and green pendulums have different natural frequencies, but 2 blue pendulums have the same natural frequency. The point is this: when I vibrate one of these pendulums, this vibrating pendulum will force other pendulums to vibrate. Force. So, when one of the blue pendulums is at vibration, I'm going to make one of the pendulums source. I'm going to vibrate it, but after a while I will see that other pendulums will also start vibrating, because the pendulums, this pendulum's vibration will be transferred to the other pendulum by this rubber band. But something surprising will happen now. Yes, all will be forced to vibrate, but some of them will vibrate with a larger amplitude, but some of them will vibrate with a smaller amplitude, even if they'll stop after a while. So now you see this simulation. This simulation is about this. But in here we have 5 in this simulation. In here we have 4. That's one difference. Source pendulum is the one on the left. Yeah, maybe you will vibrate. The one on the left. After a while, you will see that rubber band transfers the vibration from this one to others, and then it will start vibrating. But what is difference in this vibration? Try to investigate this. There's something different. Okay, let's start with the vibration. You see that? Then they start vibrating, but yes, vibrate, but stops. Vibrates and stops. Vibrates and stops. But look at this. Is it stopping? No. This one is not stopping vibration. Why? Because they have the same length. So what will happen if they have the same length? They will have the same frequency. Yani, this pendulum and that pendulum have same frequency. Then can we conclude that if 2 pendulums have the same frequency, vibration is transferred from source to the one which have the same frequency more compared to the others. These others are going to be forced to vibrate a little, force. Yani, this source pendulum forces all of them to vibrate. All of them forces to vibrate. Their force vibration is happening 1, 2, 3, all of them. However, this one, which has a different natural frequency, vibrates a little, then stops. This one vibrates a little and stops. Then a little and stops. Then a little and stops. Continuously. Stops, vibrates, stops, vibrates. A little vibrates and stops. But these two continuously vibrate. Yani they are transferring the vibration, yani energy from first to fourth, fourth to first, first to fourth, fourth to first, and so on. It goes on like this. When one pendulum, the pendulum is set in the vibration, it will force other pendulums to vibrate, but I will see that green and red pendulums will vibrate only slightly, then stop. Then only slightly, then stop. Why? Since their natural frequencies are different than blue pendulum. Blue pendulum here is the source. This is the source. Source. And what? This green and this red, different in frequency. That's why they will slightly vibrate and stop, slightly vibrate and stop. However, second group blue pendulum have exactly the same length, exactly the same frequency. What happens? The second blue pendulum will oscillate with a much larger amplitude, since its natural frequency is the same as the first blue pendulum's natural frequency. If the natural frequencies of two pendulums are equal, they are the same, this is said a fact in physics, named a fact in physics. These two pendulums are said to be in resonance. They make in resonance. What happens? Then it happens if two pendulums have the same length, same natural frequency, they are said to be in resonance. So then we can transfer energy from one pendulum to another pendulum much efficiently. Okay. So the vibrations completely transferred from first to second blue, then second to first blue, then first to second, second to first. Energy will be transferred between these two pendulums repeatedly. So this energy transfer between the pendulums repeats several times, even infinitely, if there is no damping. But damping, because of damping, of course, mechanical energy will decrease. We learned in chapter 3, section 2 about this. So finally, the system will stop. But you are going to see something. Now I will show you an experiment about this much interesting experiment. This is the definition of the resonance in your book. All definition in the book must be known. Resonance is a phenomenon that occurs when frequency of a force applied to a system, frequency of one system, vibrating system, matches frequency of another vibrating system. This is called resonance. So, frequency of a force applied to a system matches natural frequency of this system. Yani your push frequency and systems natural frequency must match each other, must be equal to each other. Then what will happen? Energy and vibration will be transferred from that system to another system. Energy is transferred from one system to another system. It will start vibrating. Energy increases, so energy and amplitude are directly even square root of the amplitude. Remember? Amplitude vibration will start increasing. Initially it will start like this, and then like this, and then like this, and then like this. So as energy is transferred from one system to another system, its amplitude of the vibration will start increasing. Okay. Now see this the experiment. This is a very interesting experiment. You see there are two groups of vertical pendulums. Vertical pendulums are not in your book. One group is on the right, other group is on the left. These two groups of pendulums are connected to each other by a pipe, which will help vibration to be transferred from one group to another group. But as you see on the left and on the right, red pendulums have equal in length, which means their natural frequencies are same. Yellow pendulums are equal in length, which means their natural frequencies are the same. Green pendulums are equal in length, which means their natural frequencies are the same. This man will vibrate groups of pendulum on the right, one by one, you will see that which pendulum start vibrating with the greater amplitude on the left. See it. He's going to vibrate first red. Of course, when red starts to vibrate, it will force all other pendulums to vibrate. But one of them, which is in resonance, will start vibrating with a greater amplitude. Red and red. Yellow and yellow. They are all are forced, but yellow and yellow, they are in resonance. Green and green. Clear? Resonance, as I said, if you want to transfer energy from one system to another system, you should set up the resonance between them. If this happens, you can transfer energy from that system to another system very efficiently. Okay? Now examples. In fact, in our life there are examples for the resonance. One of them is pushing a playground swing. Do you have little sisters, little brothers? You are taking them to the park, you are taking them to swing, you are pushing them to swing. If you don't know physics, you cannot start swing to vibrate the swing like this father. Now look at this father, let's see that. What is wrong in here? What is wrong in here? Huh? What is wrong in here? Tell me. This father doesn't know physics. If you want to transfer energy from one force to another system, their mutual frequencies must be same. Father is pushing the swing with a different frequency than frequency of the swing. But if his frequency of the push would be the same as the frequency of the swing, this father will start adding energy to the swing, and swing amplitude will start increasing. So initially he doesn't know physics, then he takes some lesson, and then he learns physics, then he fixes this. Okay, see it. Cahil Baba. Now he is taking some physics course, then learns what he should do. His frequency of the swing of his hand back and forth and frequency of the swing must be the same. The energy will be added from his hand to the swing, and the angle of the swing will increase. Resonance. One example. Second example, you can break a glass by your sound.
Oh yes, I've seen that. Vibrations.
But it is not that easy.
No, it's not.
You have to work on it maybe weeks. And you should also use the glasses which are not very thick. Adding energy to glass by sound. Everything is vibrating. Everything. Glass molecules, this building, bridges, anything around you is vibrating at some frequencies, some natural frequencies. If you can catch by sound the natural frequency of this vibration, resonance takes place between your vocal cords and that object's molecules, and you start adding energy. As energy is added to molecules, what happens? They start vibrating with a greater amplitude. Initially maybe like this, then like this, then like this, then like this, it's broken. Yes. Now see what happens. He's hitting first the glass to get the same sound, to make the same sound. Yeah? You get the same vibration. Then he tried to catch exactly the same sound. We'll try.
Thank you very much for watching.
Okay, this is a resonance. Resonance between your vocal cords and glass molecules will make these glasses to be broken. But be careful, it must be very thin glass, wine glasses,
Yes.
not usual glasses. You cannot do that. And one more example is given in your book. This is not given in your book, but this is a fun, that's why I put it in here.
Yes.
This one is in the book. Destruction of Tacoma Narrows Bridge. This bridge is constructed in 1940s. But to be economic, because 1940s the World War times, so generally countries are using their money for war, not for developing the country. So they are making a bridge in the narrowest place in the channel. Narrow, that's why it's called Tacoma Narrows Bridge. Narrower place, but this construction is horrible. It's a mistake of engineering. As I said, everything is vibrating, even the buildings, even the bridges, they all vibrate, not visible vibration. They don't. This building is vibrating. Wojcicki building is vibrating. All of them. But those vibrations are not visible to us. But in this bridge, it is visible. See.
Elegant and economical.
Yeah. When it is open, this is like that.
Move up and down like no other before it.
It's vibrating.
Just 3 months
So-
after
so-
it opened, in a steady
After 3
wind,
months.
the Tacoma Narrows Bridge began to twist as well as become
Birazdan konuşuruz. Birazdan söyleyeceğiz.
the bridge tore itself
Standing waves, you see that? Only vibrating. Standing waves formed on the bridge. But why? He put this bridge, this engineer, such a place that he didn't consider the direction of the blow of the wind. So when the wind is blowing, so bridge is vibrating like this. When the wind is blowing across the bridge, somehow, ne diyelim, God given whatever it is, God decided this. So blow frequency of the wind and vibration frequency of the bridge match each other. Yani, when wind is blowing, so it's vibrating like this. Then, after each blow, wind gains energy. And the wind gives energy to the bridge. Then when energy is added to the bridge, what happens? Its amplitude will increase. Initially it was like this. Then by time it goes like this, and then like this, and then like this, and then like this. Finally it's twisted completely. Resonance. Resonance between the bridge and the wind causes its destruction. One example is this. There's one more example given in the book, which is collapse of a section of the roadway in Auckland by earthquake waves. Earthquake waves destroy the buildings by resonance. Yes. I don't know, 2 or 3 days ago, there was a great earthquake at night. In 2018, there was also earthquake, maybe you remember that. If, every earthquake is a wave. Every wave has some frequency, huh? And every construction has a natural frequency or vibration. If the earthquake wave's frequency and natural frequency of the vibration will match each other, what will happen? Resonance will take place. If resonance takes place, energy will be added by the earthquake waves to the building. The building will start vibrating with a larger amplitude. If resonance takes place. Well, if it doesn't take place, what happens? This happened in 2018 when I was sitting at home. Initially it started a little, then stopped. Then a little vibrated and then stopped. Yani, which means there's no resonance. If no resonance, energy will not be added. That's why it's going to be forced, yes. Earthquake waves will force the buildings to vibrate. But because no resonance, energy will not act efficiently. That's why buildings will not vibrate with largest amplitude. But in this example, this bridge natural frequency of vibration and earthquake, vibration frequency match each other. And earthquake vibration frequency, and natural frequency of vibration will match each other. Then the buildings will not vibrate with largest amplitude. But in this example, this bridge natural frequency of vibration and earthquake, earthquake vibration frequency match each other. Then the buildings will not vibrate with largest amplitude. So energy is added to the bridge. As energy is added, what happens? It's broken. Another example of the resonance. Destructive example. Resonance is also a best method of transferring energy from one vibrating system to another system, yes? And at the same time it can cause destruction if you are not careful about constructing the buildings. Okay. So these two examples must be known. They give this example in your book. What of them? One of them is the collapse of the section of the roadway in Auckland, and the other one is destruction of Tacoma Narrows, which both are examples of energy transfer by resonance between two systems. And last title, sympathetic vibration. Sympathetic vibration. Oh. Sympathetic vibrations are about musical instruments. I have a guitar. Wait, anyone plays guitar in this class? Anyone who plays guitar? Do you play?
Yes.
Still playing?
No.
Really? Are you good at playing?
Not really.
Not good?
Yes,
She's good. Okay, I will send you music, okay? So when you go home, try to play it. And I'm going to blow nay, you are going to play guitar, we are going to make duet, okay? Alright? I did last year with one of the girls from 12th grade. I'm just choosing one student who is good at playing the guitar, so we do duets. Okay. So this is a model for a guitar. Guitar is a string instrument. In 4-3 we will talk about them in details. So when isolated guitar string, isolated means it's not connected to anything. Individual. Just you stretch it between two fixed points. It is isolated guitar string. This is not completely isolated, but not connected to a guitar body. When an isolated guitar string is held taut, taut means stretched, and plucked. Plucked means this. Hardly any sound is heard. You hear the sound, but intensity of the sound is not so loud. When the same string is placed on a guitar body and plucked, the intensity of the sound will increase. Okay, I have a wooden object. Guitar also has a wooden body. I will put this on the surface of this wood. Then I'm going to pluck again. Did you see the increase in the intensity? Ben bir şey yapmıyorum. Sanmayın ki ben hızlı yavaş vuruyorum. I didn't change anything. But what happened? When we connect this string to a wood, even the inside the wood is empty, area of the instrument increases, and more air molecules get in contact with this instrument. Because if I want to transfer the vibration from string to the air, which will come our eardrum, make it louder, I need to transfer this energy at a greater rate. Power must increase. By making the area larger, what am I doing? I am making the energy transfer from the instrument to the air faster, quicker. And the rate of energy transfer increases. The rate of energy transfer is called what? Power. Power of the instrument increases. If power increases, intensity proportionally increases, and then you are going to hear a louder sound. This is the reason. So, guitar body has a larger area than string, correct? String is just a string with tip. So less numbers are in contact now with this string. So energy transfer rate is not that big. That's why low power, low intensity, softer sound. But when we attach like this wooden object also starts vibrating when I plug it. So the guitar body enables the string vibration to be transferred to the air at a greater rate. Yani power, more powerful. Your book uses this word, but this is much better. Greater rate. Yani power of the instrument increases. More efficiently, it says. So as a result, intensity of the sound increases. However, strings vibration die out, yani lose energy faster. What does die out mean? So it's like this. In this classroom there are 23 students, huh? I want this classroom to be emptied through one door. If there's one door, it will take time, huh? For students to leave the classroom. But if I open more doors, like increasing the area, so what will happen? Classroom will be emptied quicker. Similarly, when you make area larger, energy of the string is given out to the air at a greater rate, which means vibration will quickly die. But if you use only string, because energy is not transferred at a greater rate, it takes time for energy to be given out to the air, to your ear. Did you get the idea? Sidra, did you get it? Are you sure? So as a result, intensity of the sound increase. However, string's vibration die out, lose energy faster. So what happened in here is this. This is a guitar example. There are strings, huh? When the guitar, what are we doing? You are plugging the string first. But string is in contact with a bridge. This is called bridge. This is called bridge. Whatever the string's frequency is, this bridge starts to vibrate with the same frequency. But bridge is in contact with what? Guitar body. Bridge transfers the vibration to the guitar body. Guitar body starts vibrating with the same frequency. Yani, string's frequency, bridge frequency of vibration, and guitar body's vibration frequency all are equal to each other. So the vibrating string of the guitar forces the bridge of the guitar to vibrate, and the bridge forces the guitar body to vibrate. So as a result of this, energies and vibrations transfer at a greater rate at the same frequency. This chain of forced vibration is called as what? Sympathetic vibration. Sympathetic vibration happens only in musical instruments. Musical instruments. Guitar, violin, cello, whatever it is. So then, from string to bridge, bridge to body, body to air. Air to your ear. All are vibrating with the same frequency. Okay? Any question? You want?
Didn't we see that area is inversely
Ha,
proportional?
bu soruyu soracak biri var mı diyordum, sordum. Not about instrument. This is about instruments area. That one is area of the wavefront which is expanding. They are different things. Yani as the area of the instrument increases, intensity given outside increases. Ama what you are talking about is as sound is expanding, what's happening? This is not about sound expansion. It's about sound production. Sound production. Tamam? Any more questions? And now we will finish this section with a sectional question, and very important question. Very important. Which of the following factors change when sound gets louder? Which change when pitch gets higher? We studied pitch. What is pitch in for what? Even you got the equation for the pitch. F prime is equal to F times V plus minus VO divided by V plus minus Vs. Pitch frequency depends on source frequency. If source frequency increases, pitch frequency also proportionally increases. One of them is the second one is relative motion. Remember. Then, if pitch gets higher, can we say frequency is getting higher? Yes, why not? We can say it. Frequency. Yani higher pitch means higher frequency, but we know frequency and wavelength are inversely proportional. If frequency of the source increases, wavelength of the wave coming from the source should decrease and shorter wavelength. It's about 4-1. Pitch part is 4-1, but now 4-2. This one is important. It says that when sound gets louder sound. Louder sound, loudness is represented by beta. Do you remember? Beta? Şuradan devam. Beta. Beta, louder sound means beta increases. If beta increases according to beta equation, I over I should be increasing. Sound intensity should be increasing. sound intensity depends on the power. Remember the power? I is equal to power divided by area. So then power should be increasing. Power is the rate of energy transfer. Energy transfer should be increasing too. Energy of a vibration or sound, whatever it is, directly proportional to square of amplitude. If energy is increasing, amplitude should be increasing too. Okay, all are increasing or all are decreasing. Louder means high intensity, high power, high energy, high amplitude. Softer sound, low intensity, small power, small energy, small amplitude. Now, this question, this is very important. Now you will see that in this question 3 or 4 times asked just about this. Only about this. Now open minister exam question page. Bitti mi ya? Sizin saatinizde sorun var o zaman.
Evet.
3 soru var ya, şunları yapalım. 3 questions, just 3 questions. Only 3 questions. Let's do them after that. Okay. Question number 10. With the 10. Page 99. Question number 10. Which of the following factors change when sound gets louder? Speed? Speed depends on medium. Frequency? It depends on the source. Wavelength? Depends on the source. And medium, not power. But intensity? Yes. Next question, question 11. Which of the following factors will change when sound gets louder? Intensity? Yes. Amplitude? Yes. Relative intensity? Loudness means relative intensity. All are correct. And 12. Which of the following factors will not change this time? Which will not change? Speed of the sound depends on the medium, not about related to loudness. But intensity, decibel level, and amplitude all are changing with intensity. And louder sound means high intensity, high decibel level, and high amplitude. But speed of the sound is not related to loudness. Clear? Yes. Good for you. Next lesson we will continue with section